So I've taken the time to redraw this so it's a little bit more to scale. I've drawn XC, the vector at 270 degrees, EC and RPC much longer, and the vectors at 90 degrees much shorter, and drawn this a little bit more to scale. You're going to see when we put the numbers in here that it's still really not, but it's a lot closer than we were before. So I've already included the numbers that we calculated. We were given the value of R, 10 ohms. We were given the value of EA, 120 volts. Put that in there now as well. And we calculated XL, XC, and then this value that we'll call X, which is the opposite of our right angle triangle. Which means we could find that angle, okay? But I think where we want to go now is let's use the Pythagorean theorem to calculate the hypotenuse of our impedance triangle and find out what our value of Z is. Okay, so I don't have room to do the math here. What I'm going to suggest is that you keep your finger on the pause button and work through this rather slowly. Okay, I just told us what the next step is. I think I'll pause, I'll hesitate, give you a chance to think about that as we go through as well. But hit pause right now, calculate the value of Z, and then come on back and we'll continue. Okay, so Z equals, I've done the work myself as well, Z equals 39.05 ohms. 39.05 ohms. I sure hope that's what you found as well. And now, once again, keep your finger on the pause button. What's the next step? We've got all of our values for the impedance triangle. Okay, so that's done. Okay, we've included even a number that doesn't go anywhere. Okay, but we have all of the numbers here. So it's time to move on to fill in some blanks on the other triangles. So how are we going to do that? Well, let's start with what do we have available to us over there? Is there anything? Sure there is. We have the hypotenuse of the voltage triangle right there. We know that that's the power supply, 120 volts. Okay, so with that piece of information, okay, related to voltage, we want to find a matching piece of information related to impedance. Okay, well what we have is our Z value. Okay, so we can only match up pieces that are on the same sides of the triangle, the hypotenuse of our voltage triangle and the hypotenuse of our impedance triangle. So if we have a value for voltage and we have a value for impedance, what can we calculate for? We can use Ohm's law to calculate for current. So I is going to equal the voltage divided by the resistance or the impedance. Okay, and that happens to calculate out to, hit pause, grab your calculator, come on back. What does I equal? 3.07 amps. 3.07 amps. And that number is across the board. No matter where we measure current through a circuit, that is the number we're going to measure. That is the current we're going to find. So I equals 3.07 amps there, and I equals 3.07 amps there. Okay? And now we can carry on with Ohm's law. Okay? I see one variable I didn't write in. E subscript R. Let's calculate for that next. Hit pause, crunch the numbers, come on back. How did you find the value for ER? Again, Ohm's law, if we're calculating for E, we need to know I, and we do, and we need to have an impedance value and the appropriate one. Well, we're calculating for the voltage drop across the resistor, so it is going to be the resistance number that we're going to be using. So, 10 ohms multiplied by 3.07 amps equals 30.7 volts. There it is right there. Okay? So now we have two sides of our right angle triangle that is our voltage triangle. Okay? We can calculate for the third. And we can do this in a couple of ways. All right, we have a couple of options here. One would be to use the Pythagorean theorem. So it would be EX equals the square root of EA squared minus ER squared. Would give us this number. That's just our right angle triangle work, Pythagorean theorem. The other option would be to calculate using Ohm's law. What does voltage equal? Voltage equals current multiplied by the resistance, the correct value of impedance. Well, if we're calculating for EX, the vector at 270 degrees, then we're going to have to use X as our impedance value. Okay, what is the voltage drop across the reactive portion of the circuit? Well, what is the reactance of the circuit? Okay, so two different methods to calculate that. I would like you to try doing both and see if you get the same number. And that number is 115.9 volts. Now we're starting to use calculated values to calculate additional values. So if your number isn't exactly 115.9, that's okay. A little bit of rounding error. You may have carried more decimal places than I did or less. Okay, but if you're right in that neighborhood, if you're anywhere between 115 and 117, okay, you're definitely on the right track. Okay, certainly I expect when you calculated this using the two different methods, you probably got two slightly different numbers. That's fine. Don't worry about it. This number, however, doesn't belong anywhere in our exercise sheets, on our answer sheets. Okay, what we need to find is EL and EC. Okay, this is the difference between the two. So we can start to recognize the scale, and we know that the ratio is going to be the same. So we could actually do some funky ratio values and figure it out. But there's an easier way. Just carry on doing exactly what we've done. We can use Ohm's law in these portions of the circuit. If I'm calculating a version of voltage, then it's going to be current multiplied by some version of resistance. Okay, current is the same, so it's 3.07 multiplied by something. Well, if we're asking the question, what is the voltage drop across the inductor, it's going to be current multiplied by the inductive reactance. And so 3.07 times 15.3 is going to give us a value of 46.97 volts. Okay? And one last time and we're done the voltage vector. And I think I'll probably stop the video there before it gets much longer. Let's find the voltage drop across the capacitor. Okay? Now this is an interesting one. This is the one that will probably hurt some people's heads. And that's okay. It's good that you're thinking about this. First of all, calculate it. I pause, you work. We come back together. What did you calculate for EC? The current multiplied by the appropriate reactance, which is the capacitive reactance, which is 53.05. You multiply those together and you get a number which is 162.886 volts. Now this is a really weird one because look at this. We have calculated a point in our circuit where the voltage is 163 volts almost, when the power supply was only 120 to begin with. It's a bigger number than our power supply. How is that possible? Well, the easiest way to explain that is that this is really a theoretical conversation. Okay, we have tried to pull the capacitance out of the circuit and temporarily ignored the fact that, remember, every electrical device offers some resistance. Okay, it's not a perfectly capacitive device. It offers some value of R. And so this number, this vector, is really kind of theoretical. Okay? And so don't think any harder about it than that. Okay? We did the math, it works out, everything falls into place. Okay? We're good. All right, this is kind of just a a math exercise, not perhaps terribly realistic. Okay? Let's pause the video there. Carry on and calculate your powers. Okay? The other thing we need to find is the angle and the power factor, and then we'll be done. See if you can finish that before you watch the next video.